Very good. So we have been talking about rock magnetism, the properties of the magnetic properties of rocks and minerals, and we have kind of subdivided rock and minerals into three basic categories: diamagnetic, paramagnetic, and ferromagnetic. And in ferromagnetic family, we have seen ferromagnetism, antiferromagnetism, spin-centered antiferromagnetism, and ferrimagnetism. Okay. We talked about Curie temperature. We have talked about the Curie temperature of common rock forming minerals. So you need to remember the basically for these oxides, what are the general Curie temperatures? What is it for pyrrhotite? What is it for magnetite? What it is for hematite, rutile? Okay, so that is given in Lowry's book. You can scan it through, but you should have a fair idea of what are the range of Curie temperature for common oxides which are responsible for susceptibility in a particular mineral or a rock. Now, we have also introduced you to something called magnetic moment. And we said that, they could be randomly oriented, but upon the induction of external magnetic field, they try to align themselves along the direction of the external magnetic field. And hence, magnetization occurs in a particular rock or a mineral. Now, of course, how much magnetization will it acquire depends on a particular parameter, which is susceptibility. Okay. So now, if we look at the ferromagnetic minerals, okay, a very common test is done. Ferromagnetic minerals, a very common test is done is to create hysteresis loop, okay? And you all know about hysteresis loop, but we will anyway look into it once because it is something which is relevant for rock magnetic understanding, and this is often done as a routine procedure in any rock magnetic laboratory. Okay, so what essentially happens that I have a rock sample, okay, and then I subject that to external magnetic field, and I keep on increasing the strength of the external magnetic field, okay, and then I measure magnetization. Okay, so what generally happens? So suppose this is external magnetic field, which is H, and this is the acquired magnetization or induced magnetization, which is M. Of course, we know M is equals to KH, and K is the susceptibility. So I keep on increasing my H, and I see that my magnetization is keep on increasing as well. And then after a while, it reaches a plateau. Okay. So why would it reach a plateau? So if I want to understand it physically, what it means that it starts with more random magnetic moments, right? This is where you don't have a induced magnetic field, or the value of H is 0. And if I keep on increasing the H, what happens? These magnetic moments would try to keep on aligning along H, and there will be a time when most of them will be more or less aligned. Okay, and if I then further increase H, there will be not any significant change in my acquired magnetization because it has already reached saturation. All the magnetic moments that could have aligned as per H has already been aligned, and then it will not increase the magnetization magnetization anymore. So you can kind of join them with a line. Okay, and so you can see here the plateau is reached, and this is what we called as MS, This value is called ms, or this is also said as saturation magnetization. Okay. Okay. So once the saturation magnetization is reached, what we essentially do, we reverse the magnetic field. Okay, we reverse the external magnetic field, which is H. Okay. Now, if I reverse the magnetic field, what would happen? I will keep on decreasing my magnetization. Okay, I'll keep on decreasing my magnetization. That means the magnetic moments are again getting randomized. Okay, but the magnetization will not follow the same path. It will follow a different path. So this is my forward path of magnetization. This is my backward path of magnetization. And then, even if I make my H, that means external magnetic field 0, okay, if I make my external magnetic field 0, okay, I will see that I am still left with some magnetization, okay, and that is what we call as MRS, or isothermal remanent magnetization. Okay. Why is it called isothermal? Simply because this whole experiment is done on a single temperature, and generally that is room temperature. So the temperature is not changed. The temperature, the ambient temperature of the experiment remains same throughout the experiment. Hence, it is isothermal and isothermal remanent magnetization. So what is significant about isothermal remanent magnetization is that although I have, while reversing the field, I have made the external field to be 0, okay, but still what I am observing that my um, so what I have done, I have essentially decreased my external magnetic field, and now my external magnetic field is 0, but I still see that my there is some magnetization left in the sample. Okay, and that is what we call as isothermal remanent magnetization. What it means physically, that although I am removing the external magnetic field, not all the magnetic moments are able to turn back to its completely random position. Okay, there is still some alignment left within the system, and then I make my magnetization negative, I mean opposite, and then I slowly see that there is a point at which the magnetization, sorry, the acquired magnetization becomes 0. Okay, so this value of external magnetic field is called HC. Okay, HC, or coercive force. This coercive force is a very important phenomena which we will discuss in a moment. So this is what we call as coercive force. And then if we further, keep on increasing in the opposite sense, what I observe that after a while there is plateau reached again, but on the other side, okay, and and then if I continue this one, again, if I start increasing my magnetic field, this is how the magnetization occurs. Okay, and so this is what we typically see in this is what we typically see in an hysteresis loop experiment. Now, if I simply kind of project this part of the graph on this side, this will kind of meet somewhere here. The first forward moving curve, if I project it on the other side, so will meet somewhere here, and this value is called HCR, or remanent coercivity. Okay, this is what we call HCR, or remanent coercivity. Now, is this clear, guys?
Yes, sir.
The typical hysteresis loop experiment. Okay, very good. Now, I wish to bring another important concept, which is called the domain structure okay. Now, let us say I am looking at two ferromagnetic grains. One is of a considerable size, maybe of around 100 microns or so, okay, fairly large. Okay. And I'm looking at something which is extremely small, which is say 1 or 2 microns. Okay. Now, what happens if my ferromagnetic, maybe this is, let us say, this is a magnetite grain 1 and magnetite grain 2. Okay. So, what happens in case of if the grain size is larger, what it can contain number of magnetic moments. The same magnetite grain will have a number of magnetic moments. And such grains are called multi-domain grains. Okay. And then there is something where you have a very small tiny magnetite grain, and in that case, of course, it can contain only one magnetic moment, and that is what we call a single domain grain. Now remember, if a rock sample has dominantly more multi-domain grains, a rock sample with dominant multi-domain grains, MD grains, okay, it is very easy to magnetize that sample, easy to magnetize. Also, very easy to demagnetize. Okay, what do I mean by that? That these magnetic moments, if they are multi-domain, what has been observed that these magnetic moments are very what should I say? They are very easy or free to move. Okay, so you can very easily align them with an external magnetic field, and you can very easily demagnetize it. That means you can randomize them also very easily. Okay. On the other hand, for single domain grains, it is very difficult to actually do the same thing. It is very difficult to magnetize. It is also very difficult to demagnetize. Okay. Now, there is something in between, that is what we call as pseudo single domain. Okay. So these are like multi-domain grains, but the size being kind of in between multi-domain and single domain, they kind of behave like single domain grains. Okay. So hence they are called pseudo single domains. Now, you tell me one thing, that I am looking at two situations. Okay. In one situation, so this is my MS, that is means magnetic saturation. saturation magnetization, and here is my MRS. Okay. Here is HC, and hence here is HCr. Okay. And let's I mean, you can let's forget about HCr for the time being. Let's just say in one case the HC is here. Okay. So this is case number 1. Okay, and in case number 2, I'm not drawing the hysteresis loop. You can figure out how the hysteresis loop will look like, but here are my constraints. Okay, and in the second case, here is my MS, here is my MRS, and the HC value is fairly large. Okay. So, can you tell me which one is? Let us just look. Okay, let's just let me not complicate first. Let me just use it very easily. Now, if I have two cases, in one, HC is smaller, and in the other case, HC is larger. Okay, can you tell me in which one I have? Which one of them is actually a single domain grain, and which one is the multi-domain grain dominated rock sample? Can you tell me?
First one is first one is first one is shortly.
So HC is smaller here and HC larger here. Which one is the rest of it is are the same? So which one will
So
be
no, first
multi-domain?
multi-domain is second. No, first one.
So how many
Sir, the
of you?
first one is multi-domain.
And
When
why do
I
you say so?
So
because it
because it is
is
easy to magnetize.
easy to demagnetize and magnetize.
It is easy to demagnetize, right? So I actually require less uh, opposite force to actually demagnetize the sample, isn't it? So less amount of oppositely directed external magnetic field, isn't it? So that's why if I have smaller HC value, that means this is multi-domain. And if I have higher HC value, that means it is perhaps single domain. Okay. Now, if I look at the same situation, so now let us do the same thing. So suppose I have one situation where this is MS and this is MRS, and MS, MRS. So in one case, of course, I can see my saturation. So MRS by MS. So this is, this. So in one case, MRS by MS ratio is higher than the other. Okay. So which one will be multi-domain? Which one will be single domain?
So first one is multi-domain.
Why?
So because we can see the ratio is smaller, so we can see also that it can easily be magnetized and demagnetized by this ratio.
So what do you mean by that? So is it so that means that I did not understand exactly why this will be multi-domain. Does everyone agree that this will be multi-domain?
Sir, I don't understand it. Can you please explain?
So in the first one, the ratio of MRS. So in one case, the MRS, so let us say MS is constant, okay? So in one case, the value of MRS is higher, and in another case, the value of MRS is lower. Okay, this is the saturation magnetization. Sorry, isothermal remnant magnetization. The magnetization that is left within the system. So which one is single domain? Which one is multi-domain?
Okay, sir. The first one is single domain. All right.
Why do you say so?
So because if we can see from the origin, the remnant suspension is high. So we can conclude that it uh, it is single domain because as you said, single domain has hard to magnetize and demagnetize. So it will remain more saturation remnant.
Anyone has any other opinion? Hmm? Let me hear it.
Sir, even I also agree that maybe the one on the left is the single domain grain.
Okay. Anyone else? Okay, think about it and let me know in the next class. Yeah, read it a little more and let me know in the next class. What do you think exactly? All right. Now, there is something called, what should I talk about next? Let me, just give me a moment. Let me see which one I should talk about. So in this regard, there is, you will not find that in Lowry's book. There is something called days plot. Okay. Okay. So what days plot does? Days plot actually essentially plots MRS. Sorry, MRS by MS in one ratio, and in other one HC by HCR, okay, in the other axis, and then it subdivides the whole field into single domain, multi-domain, and pseudo single domain grain. So please read about Day's plot. This is part of your homework, and then tell me if it makes sense with the logic that you have been giving me. Okay. So find out about Day's plot now. Where is that? Let us say I take out a rock sample Okay. And then I analyze its magnetization. What is magnetization? How do you define magnetization? Can someone tell me? What is magnetization, by the way?
So property to magnetize something.
No, no. How do we I mean, what is the mathematical expression for magnetization? If I want to express it in terms of magnetic moments. Is the summation of M i's by V. Do you remember? The summation of total magnetic moments divided by the volume, right? That is what we call as magnetization, or the average magnetic moment per volume. Okay, right? So that
Yes,
is
sir.
what we call as magnetization. Now suppose I take out a rock and then I measure its magnetization, and suppose this vector is magnetization. Okay. Now this would have essentially two components. Okay. Now, if I take out a rock simply, and then I measure the magnetization, that is what we call as NRM, okay, or natural remanent magnetization. NRM or natural remanent magnetization. Now, NRM would have two components. One we call as the primary component. Okay. The other one we call as the secondary component. So the primary component is essentially the component that is acquired by the rock during formation. Okay. So if I think of a igneous rock, it is while that igneous rock actually formed from a molten magma or molten lava, and it got quenched, and as per the magnetic field of the then magnetic field of the earth, okay, it acquired some magnetization. Okay, and that is what we call as the primary magnetization. Now the rock has been there for a long time, and it has been exposed to various changing magnetic field of the earth, and hence it has also acquired some magnetization which is not primary, which has not been there since its formation, okay, which were acquired by the rock because of it being there since its formation till today. Okay, so that is what we call as the secondary magnetization. Okay, so NRM will have two components: primary remanent magnetization and secondary remanent magnetization. So now in few cases what can happen, that if I resolve, I can see that my primary remanent magnetization is fairly dominant. Okay, sorry, I should draw it little smaller, of course, because it cannot be larger than where is it? It cannot be larger than uh, my original component. So the primary remanent magnetization is fairly large, but the secondary remanent magnetization is actually very small. Okay, so if I want to study primary remanent magnetization to understand the formation of that particular rock, I can simply ignore the secondary remanent magnetization. Okay, but it can so happen that within a particular magnetization vector, of course, my secondary magnetization is significant. Okay, and then I have my primary magnetization. Okay, in those cases, of course, I have to find a way to actually get rid of this secondary magnetization from the uh, from the uh, from the rock, so that I can actually study primary magnetization in a more robust way. Okay, so any rock, if I just collect it from the field, and then if I study its magnetization, that is what we call a NRM, or natural remanent magnetization. Now, natural remanent magnetization has two components. One is primary remanent magnetization and secondary remanent magnetization. Primary one is the one that is thought to be the one which is during the formation of the rock, and then of course the secondary is the one that is acquired. Okay, is that clear, guys?
Yes, sir.
Okay. Now, the primary remnant magnetization, in case of igneous rock, it is called thermoremnant magnetization. So, thermoremnant magnetization, so that means I have a molten magma. Okay, I have a molten magma, and then I am keeping on segregating my mineral phases according to a particular reaction series. What that reaction series is called? So if I have a molten magma and then I form igneous rocks from it, so it follows a certain reaction series of the fractionation of minerals. Okay, what does that call? How is it named?
Barnes reaction.
Bowen's reaction series. Okay, so as per Bowen's reaction series, I am forming different rocks and minerals from a molten magma. Okay, now say for example, I have now crossed the, so suppose this was at 1000 degrees centigrade or so. Okay, and then as I am cooling down, I have crossed like 675 degrees centigrade. What is 675 degrees centigrade? What is the significance? What it is? 675 degrees centigrade is what? Tell me, we talked about it yesterday.
Curie temperature
Of
of
Curie
that rock.
temperature of?
Sir, of that rock, igneous rock that has been.
No, of a particular mineral.
Okay.
What is it?
Hematite.
Hematite. Excellent. So this is the Curie temperature of hematite. Okay. So now, suppose I have already, got hematite in the system. Okay. So, so from the molten magma with temperature decreasing, I have deposited hematite. Deposited is not the right word. I have formed this hematite mineral, hematite crystal in the rock. Now, as soon as it actually crosses 675 degrees centigrade temperature, the Curie temperature, it acquires magnetic field. It acquires magnetization. It acquires ferromagnetization, to be more specific. And that magnetization will be acquired as per the magnetic field of the earth. Whatever magnetic field right at that point in time is present, the magnetic moments will align themselves according to that magnetic field. Okay, so and this particular magnetization which is now being acquired is called thermal remnant magnetization. Similarly, if I go to 578 degrees centigrade, so I had my magnetite grains already formed. Okay, at 578 degrees centigrade, the magnetite grains then start to acquire magnetization depending on the magnetic field of the earth. Okay, now this 675 to 578 degrees centigrade transition has not happened over millions of years, right? It has happened fairly quickly in most of the situations. So the hematite and the magnetite which has formed, they will acquire similar magnetic properties. Okay, similar magnetic field, and this is what we call as thermoremanent magnetization, and that is acquired by, this is the primary remnant magnetization that is acquired by the rock during the cooling process. Okay, now this is what this is what is for thermal remnant magnetization. Similarly, we can talk about sedimentary rock, and for sedimentary rock, this is what we call as uh, depositional remnant magnetization. Depositional remnant magnetization. Now, in the earlier case, what we said, because the temperature was getting down, because the temperature was like uh, was cooling down, and it crosses the Curie temperature and it acquires magnetization, or aligns themselves according to the magnetic field. Now here the temperature is not high, right? Depositional remnant magnetization, the sedimentary depositional processes do not really happen at that temperature, okay? For these magnetic minerals to change its inherent magnetic properties. You agree with me or not? Yeah? Does sedimentation happens at 675 degrees centigrade?
No.
No, right? So that Curie temperature change and acquiring magnetization, that doesn't take place in case of depositional remnant magnetization. So what happens in depositional remnant magnetization is, suppose I have a very small ferromagnetic grain. Okay, suppose I'm giving the example of a ferromagnetic grain. Okay. Now this ferromagnetic grain is trying to settle down. Okay, suppose this is a aqueous media through which this particular ferromagnetic grain is trying to settle down to the process of sedimentation. Okay. Now there is, I mean, think about this to be a small little magnet, okay? And then I have this external magnetic field. So what would happen? This will try to mechanically align itself, okay? Mechanically align itself according to the direction of the external magnetic field. Okay. Now, so it is mechanical alignment of the grain itself, okay? It's the mechanical alignment of the grain itself according to the direction of external magnetic field. Now there is one problem though. While this alignment happens, there is another force, okay, which is the mechanical force of the system itself. Suppose the water, so the water is churning, the water is flowing, the gravity is trying to do something else, okay? So all these things are actually trying to counter the effect of the magnetic field, okay? But then it's like a bit of a battle going on, and then sometimes we do find that in depositional remnant magnetization, that these magnetic grains actually acquire, kind of align themselves according to the direction of magnetic field, the then magnetic field, okay? Now, of course, because of these mechanical forces, you encounter two types of errors. One is called declination error. Declination error means, suppose the magnetic field is this way and the grain was supposed to be oriented like this, okay? But then the water came, and then now I have grain oriented like this. So here, this is what it should be. This is where it is. So I have like a delta theta. And this is what we call as declination error. Similarly, for example, if this particular grain is being settled down at the equator, then I should expect that the grain would settle down horizontally, right? If it is only because of the magnetic field. And if it is in the pole, it would actually settle down vertically, okay? If it is only because of the uh, magnetic field of the earth. And this value is called inclination, as we had talked before as well, okay? This is the angle between the horizontal and the magnetization, if you like, or the physical orientation of this grain in this particular case. Now, of course, so this is supposed to be horizontal in the equator, but then I have my mechanical force, and that is trying to do something with this particular grain as well, and that kind of deposited it with an angle. So there it makes an angle d phi or d theta, whatever. And this is what we call as inclination error. So always when you do DRM or depositional remnant magnetization, this is how its short form is DRM. The short form is thermoremnant magnetization is TRM. Similarly, this is what we call as DRM. We must actually take in account the declination and the inclination error, and there are processes by which you can actually get rid of them to the best you can. Okay? But there is another type of DRM which actually kind of nullifies this effect to some extent, and that is what we call as post-depositional remnant magnetization. Or this called small PDRM, okay? PDRM. Now think of a situation that I have, these larger grains which has already been formed. If I try to measure their magnetization, that would be DRM, and I will have the inclination and declination error there. But then after these large grains have been deposited, there are smaller grains that would deposit within this interstitial space, right? Now you see, they will be aligned according to the direction of magnetic field, but they are kind of protected by this framework of larger grain so that the mechanical forces do not disturb them much. Okay, so if I give you a rock sample, okay, and I ask you to actually find out the the depositional remnant magnetization, you should actually concentrate on the very smaller grains which are present within the interstitial space, because those interstitial spaces are supposed to be protected mechanically, are supposed to be protected by the larger framework of grains from these mechanical forces, and they can align themselves pretty easily with respect to the direction of external magnetic field. Does it make sense, guys?
Yes,
Did you
sir.
understand the difference of DRM and PDRM? Yeah?
Yes, sir.
Very good. Now, so we have talked about the igneous rock, we have talked about sedimentary rock. Which rock is left then? Which rock is left? Metamorphic rock,
Metamorphic.
right? And for metamorphic rock, we use a term called CRM, or chemical remnant magnetization, okay? Now, you can argue whether chemical remnant magnetization should be regarded as a primary remnant magnetization or it should be a secondary remnant magnetization, simply because metamorphism is altogether a secondary process, right? So you need a precursor rock which is either magnetic or, sorry, magmatic, I mean igneous, or it has to be sedimentary, a precursor rock, which is exposed to the changing temperature and pressure of the earth, and then it forms a metamorphic rock. Okay, so the rock which has already acquired the primary remnant magnetization is already acquired through TRM or DRM or PDRM, right? Now CRM is a chemical process that happens, I mean, it is acquired during the metamorphic event. Okay, now if you think that metamorphic event is kind of the it's the way you look at it, basically, if you think that the metamorphic event is actually the start of the formation of the rock, then you can treat it as a primary magnetization. But if you think metamorphism is a secondary process, then you have to treat this as a secondary remnant magnetization. In this particular case as well, while these chemical changes do happen, so new crystals do form, and exactly the way it happens in TRM, while it crosses QD temperature, the rock acquires magnetization. Okay, and this is what we call CRM, or chemical remnant magnetization. This is clear, guys?
Yes, sir.
All right, very good. That simple things. Okay. Now, so magnetization of a rock is measured with an instrument called magnetometer. Okay. So until 1940s, the magnetometers were like mechanical instruments that actually balance the torque of the magnetic field on a finely balanced compass needle against restoring forces provided by the gravity or by the torsion in a suspension fiber. So you remember we essentially discussed about the torque, right? So ideally, the basic principle of a magnetometer is you have a magnetic needle which is kind of set at equilibrium, and then you take it to a place where the magnetic field is different, and you see that the magnetic needle essentially, try to align itself according to that particular area of magnetic field. Then you calculate the torque. Okay, the torque can be measured, and from the measured torque you can actually calculate the magnetic moment, and hence magnetization. Okay, this is the basic principle of a working magnetometer. Nowadays, with digital technology, there are plenty of magnetometers which are present. I will give you some names. It's not mandatory to memorize all of them, but for your own interest, you can read through the basic principles of these magnetometers. One is called flux gate magnetometer. For your own interest, you can read about them from Laudi's book or any other book for that matter. Then you have proton precision magnetometer. Okay. Then you have absorption cell magnetometer. Okay. Now, if we talk about magnetic surveying, how it is generally done, the magnetic surveys are generally airborne. Okay. So in case of gravity, what we used to do, we used to take the gravimeter at a particular place. So it used to be point measurements, right? You remember it is actually point measurement, right? Now in case of magnetic field, the survey area is generally pretty large. What you generally do, you have a helicopter. Okay, this is in land. Okay, sorry, this is a small plane or a helicopter. Just think that this is a plane, huh? Don't laugh at my drawing. Think this is a small plane. Okay, and then from that small plane or a helicopter, there is a magnetometer that actually hangs. Okay? It's as simple as that. And then this magnetometer essentially, suppose this is the area which I need to survey. What I do, I kind of fly that plane along some grids. First like horizontal, and I mean first like east west, and then like north south. Okay, So at along all these lines, now I have data for the value of magnetization, the gross magnetization. Okay, that is what I have acquired along these lines. Okay. Now what I can do, so I have the data for these lines. Now what I can do, I can actually simply extrapolate the data in between. Depending on what data I have acquired along these lines, I can extrapolate and I can have like a 3D map, sorry, a 2D map of the magnetic values. Okay. Now, if I have more number of sweeps, these are called sweeps. So suppose, if the aeroplane does more for the same area, if the aeroplane does this very frequently, okay, more number of sweeps, then of course the quality of this data is better, simply because I have more data points to actually extrapolate. Okay, and if I have less number of data points, of course the quality of this map will be lesser. But then magnetic surveys are very commonly used in all mining and oil and gas industry, because it is very cheap to actually carry out, and it covers a large area within a very short period in time. Okay. Now you can also tag this particular magnetometer. Uh, so this is my ship. Okay, you can tag it with a ship as well, and you can do similar surveys in the ocean. There is a more modern technique that you actually hang, two magnetometers. Okay. And the idea is essentially that you try to find the difference between these two, and that would provide you some more information about the magnetic properties. Okay. Now, like in case of, you understood about magnetic survey, right? What is done in magnetic survey?
Yes, sir.
Did you understand? Okay, this is very easy. Now, in case of gravity, we used a standard for G normal. What was G normal? What is it reference to? The normal value or the theoretical value? It is reference to what? International reference
International.
ellipsoid, right?
Yes.
Similarly, the Earth, similarly for the magnetic field of the Earth, we also have, for the same ellipsoid, we have something called IGRF, and that is International Geomagnetic Reference Field. Okay. This is the International Geomagnetic Reference Field. This is the theoretical value of magnetization at any point in the Earth. Okay. So this is the theoretical value. This is the IGRF. And then I have the measured. The blue line is the measured. Okay. This is the measured. So what are these then? What are these then? The area which protrudes up, how do we call them then? The difference between measured minus IGRF, how would we call them then? Guys, tell me.
Magnetic anomaly.
Magnetic anomalies, very good. So obviously, higher, I mean, if it is higher than IGRF, that means I have a material which is slightly more, has a more magnetic properties than, I mean, slightly more magnetization. So higher magnetization means, it could be iron, nickel, or cobalt rich core, or so something which is metallic, which would have a magnetic anomaly than something which is non-metallic. Right? All right. So I will stop here today because the time is. Do you have some 10 minutes or you have a class? Then I'll just finish one thing and then.
Sir, we have mineralogy
All
next.
right. Okay. Oh, okay. 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 Then I will stop here, and then yeah. Tomorrow I will not send a pre-recorded lecture because the next thing I wish to actually have a live interaction. And tomorrow also Ganesh Chaturthi, and you have your what is that called? Quiz. So I will see you for quiz. I mean, I'll send you the quiz on Tuesday, 12 to 1. That's what we did agreed, right?
Yes, sir.
Excellent. And I'll see you on Wednesday then. Thank you very much. Bye.
Thank you, sir.
Thank you.